Hey everybody, welcome to Field Trip Friday. I'm Nick Raymond, the camp director for Maker Camp. Today we've got an awesome program scheduled out, so before we get into it, I'd like to introduce OpenROV, David Lang, and Eric Stackpole. How's it going, guys?
Hey, thanks, Nick.
Glad you could be here. And we also have the junior counselors, Josie Rushton and Jillian Benary, hanging out with us today.
Hey guys, how's it going?
Good. And so today, as always, we'll be hanging out with National Geographic, and if you have questions or comments, go ahead. We'll be taking your comments from the Make team. Leave us in all caps questions under the bottom of the post. We'll take those questions, and if you have answers or comments you want to ask us during the hangout, all caps do answers. We'll take those questions from you, and Josie and Jillian will be reading them as we go live. And then, as always, let's have some fun, and I'm going to kick it off to the National Geographic remote imaging labs today. Hey guys in the lab, how's it going? And what are we going to learn about today?
Cool. Hey guys, I'm Alan Turchik. I'm one of the mechanical engineers here at the National Geographic Remote Imaging Lab. And today I'm going to be showing you our balloon camera system, and also we have an octocopter in the back. So I'm going to start out explaining this balloon system. This is an aerial camera platform. There's a balloon that takes us up in the air, hooks to those 3 points here, and so this goes up in the air a few hundred feet, and it's mostly for getting those kind of like really cool high altitude shots without having to use a helicopter. So there's a gimbal down here. This is a carbon fiber frame that we have, and it's got some RC servo motors that control pan and tilt, and it's hooked up to right now it's hooked up to a Canon SLR camera, and we have a live video stream that'll actually be sent from the camera, so you can kind of get like a through the lens view of what you're taking a picture, and that image gets streamed down to our base station on the ground. This is a patch antenna that we use to receive the image, and then that actually gets transmitted to this controller here. There's a screen on top, and then you can kind of control pan and tilt of the camera, so you can move it around and find that perfect shot and then take it. Actually I can turn it on and kind of show you guys real quick. You can watch it. It's a basic pan and tilt rig, so you can see there's the tilt and then the pan. And this back here, that's our antenna actually streaming from the video transmitter. It's also remotely shutter activated, so if you can hear that, you can hear that's the pictures being taken. And so that's our rig. It's been used in Delaware, or an earlier version of this was used in Delaware to take pictures of it was a park, kind of to get like a totally different perspective, like in the fog, and there's this river. It's pretty cool shots. So let me go ahead and take you around to our octocopter over here. So this is a large octocopter that we built. It's all fabricated in-house, and it's to kind of get those shots that you wouldn't normally be able to get with if you want to take like a big jib equipment or whatever out into the field. So this is kind of like you can get like an infinite boom shot. Underneath, down below, you can kind of see this is a pan, tilt, and roll stabilized gimbal here. So we can put a regular SLR camera on there, or like a small Sony Handycam, fly it around and get some cool shots. It's pretty big and beefy and can carry a lot of weight. We've got 8 rotors on here. It's an octocopter. It's controlled. We have the controller board here. We use a hoverfly control board. So there's lots of parts, and in this whole thing, each arm is individually dampened. We have flexane inside each of these arm clamps here. These are carbon fiber arms. Same kind of flexane mounted in the arm clamps here for the motors to kind of take any vibration, because helicopters like to vibrate a lot. So we want to take all the vibration out so that none of that vibration is transferred to the camera, so you get as smooth as possible aerial shot. The only thing is, sometimes the helicopters crash, and that can be like, it's a lot of work to put those back together. And we actually have a video of one of those times where that happened. It hurts to even just hear that sound, that crunch, like I don't like that. But so cool. That's kind of our aerial video systems that we have. I'm gonna throw it over to Eric right now, and he's gonna show you some of our underwater stuff.
Hi, I'm Eric Birkenpass. I'm an electrical engineer down here in the shop, and basically this thing that's in pieces behind me is an underwater camera trap, but it's an underwater camera trap that can go all the way down. It can go to the very 12,000 meters, 7 miles down to the bottom of the Mariana Trench if need be. And we kind of been kicking around this idea because this thing here is it's called a glass instrument housing. It's used for like scientific instrumentation for like ocean exploration, also flotation for underwater submersibles. And glass is clear. We can put a camera in and look out. So this bottom hemisphere that you see here is actually been polished, and it's an inch thick of borosilicate glass. We stick these two hemispheres together and put a camera inside, and the hemispheres, the seal is actually formed by glass-on-glass interface, and the pressure of the ocean keeps it all together. And the beauty of glass is it just gets stronger when you squeeze it. So it's borosilicate. It can take 16,000 psi, and well, eventually, we found out eventually it'll actually fail, but you can use it over and over and over at depth. But we took it to a pressure test facility in an early prototype, and we pressure tested it to full ocean, and the glass actually failed and took their pressure test facility offline for about a week because of the shock wave that was generated. And they gave us a little bag that used to look like this. They gave us a little Ziploc bag full of sand, which was kind of a bummer. But we got past those issues and made the glass thicker. And basically, we designed the system to be completely autonomous and self-contained. So what you do is you take that camera, you push it over the edge of a boat, and it can be a small boat. It's tetherless. It goes all the way down to the bottom. And it's tied to a ballast weight. Sits on the bottom for a while, you bait it, and then it films and turns on. It has very bright lights, and any fish that come up to check out the bait, we capture on actually a Sony Handycam. This is actually a really good camera. We found out it has great light sensitivity. It works really well shooting your birthday party in your not well-lit living room, and it turns out it works really well in the deep ocean. And produces like very, very clear, crystal clear images, which you'll see in a second. But inside of this sphere is this computer, this embedded computer that controls the camera and the lights. And on the top, this is actually the top hemisphere, there's a satellite transmitter. It'll allow us to track the instrument anywhere in the world. So if it pops up somewhere and you had to leave because of a storm or something, which we had to do once, it'll transmit its location to you. It'll send me an email for a year every time it gets a fix. And then there's a VHF transmitter on board, which is a really low-tech way of tracking things that are lost in the ocean, but it happens to be extremely reliable. So we use it all the time. We wanted this to be as reliable as possible. We've only actually we built 5 of them, or 6 of them, and we've only lost 1. And basically we got some really cool video. We took it to the Mariana Trench last August, and actually beat James Cameron down there by a few months. So you want to show that video? So there's the camera going in the ocean. We just drop it over the side of the boat. So it can be any size boat. We sometimes rent small sailboats. And that time we actually saw the deepest xenophilophores ever seen. It's the largest single-cell organism in the world. It's thought to be everywhere in the ocean, and it was just the deepest it's ever been seen. And there's very few specimens available. We also saw the deepest jellyfish ever seen, which is kind of crazy. No one's ever seen an actual jellyfish down 10,000 meters down. So it seems like every time you throw this thing in, you make a new discovery. We've discovered like probably half a dozen species at this point with it. So, and then kind of a spin-off of this, we took the lights and we were like, well, let's make the lights more. So Mike's going to talk about that.
I'm also an engineer with the remote imaging department, and I'm Mike Shepard. And yeah, like Eric said, one of the things that grew out of the deep ocean drop cam was this, and this is just a big freaking light. It's everything the drop cam was with the camera removed, and then this is the prototype. It has about 1,200 watts of LED light, which is a lot for LED light, and it's based on the same glass sphere thing because it was cheaper for us to do, and it provides the flotation. It's computer controlled, and it has about about a kilowatt hour of battery capacity in it. So it can also vary its light output and run a pre-programmed thing. And we've used it on a couple of shoots to provide lights for like auxiliary lights for ROV shoots and things like that. I can turn it on for you. It's this is like 1% of what it can do, and it's like a night light at this point. But at full power, it's over 100,000 lumens. Which this one you're not going to see all the lumens because the bottom half of it's smashed, which is why it's still actually in the lab for people to see because it got destroyed on an air flight to Mexico. And the other two complete ones that are actually brighter are in Mexico for a cave shoot that Eric will be on soon. So that's everything it can do in its smashed, half-covered state. But it's probably, when it was made, was one of the brighter LED objects around the world. The other thing, let's see, that's it.
Yeah, talk about the critter cam.
Oh yeah. So one of the core things that the remote imaging lab's done over the last decade or two, or at least two, is the critter cam, and that was our original purpose for the creation of our department was animal-borne imaging for remote imaging and mainly for behavioral research. And this is the critter cam, and this is the clamp that you need to put it on a great white shark. This is a fake wood fin sculpted to be a great white shark. And what it does is like a cable tie, and there's a gun that we made that's like basically a really large zip tie gun. It's about 6 feet long, and you hang off the boat and try to get the shark to come to the surface with a piece of meat and clip it on as it goes by. And it sounds dangerous, but it's actually way safer than the first way we put cameras on white sharks, which was either like trying to do it by hand or with jab tags or all kinds of things that have gone badly before. So I guess we're going to see a video of us trying to put cameras on white sharks. Eric and I have been trying to put cameras on white sharks 200 miles out on an island called Guadalupe. After the 5th day of trying to put cameras on white sharks, you sort of start to forget that they're white sharks. And the shark sort of turned and came straight in. Full force hit the motor, pushed the boat at least a boat length backwards, and I just fall directly in the water, with the white shark sort of right there.
I was sure I was going to watch him get chomped in front of me, and I was going to have PTSD for the rest of my life. So, yeah, it's definitely an animal to be respected. So, yeah, that was a video of Eric and I putting cameras on white sharks, and it doesn't always go that badly, but we had actually put lots of cameras on lots of sharks before that. It's apparently the only time anything like that's like really made it on YouTube for us was me falling off the boat. Like all the clips of us doing it right aren't nearly as popular as me falling off the boat. So, you know. This next clip, I think, is one of the where we actually did manage to get a camera on an animal, and it was one of these times when I didn't actually think it was really going to work. It was this is a camera on a squid. So in order to actually see anything underwater, you need light, and we were of the opinion that most marine animals couldn't see red light well, but it turns out that squid can see red light well, and it's their fight color or something. So this squid actually pulls the camera off this other squid and tries to eat it all the way until it floats to the surface. So then in the next try, we actually turned the lights off and did a shallow deployment where the squid happened to not be very deep. And it actually worked really well without the light. But,
show them where the lights come out.
Oh, the light actually, this camera is also an embed. It's got a computer and it's got lights in it. So right around the camera, there's these red LEDs. We can make them any color, but we were trying to use the least obtrusive color, which we thought was red, but in the case of squid is not. any color is apparently the fight color, I think, for squid. So I guess that's all we've got from the lab and for this segment.
Great, thanks guys. I think now we're going to toss it over to the OpenROV guys. David and Eric, how you guys doing?
Good, thanks. Great.
And what do you guys have over here? What is OpenROV and what are we looking at?
Cool, thanks. Well, I'm Eric, David, and yeah, we're the OpenROV team. We've got this do-it-yourself, open-source, remotely operated vehicle. That's kind of a fancy word for a robotic submarine. We've got it right here. As you can see, it's this little robot about the size of a shoebox, and it's got a little camera on board, and it's waterproof, and it's got these motors with propellers in the background. It might be a little bit hard to see here, but basically, you can drive this around underwater and look at stuff that's down there, kind of like playing a video game. You have a control console on the surface and a video screen, and you just kind of drive it around and explore.
So like a lot of the stuff that we just saw with the National Geographic Remote Imaging Lab is amazing, amazing technology. But we're trying to make this as cheap and as accessible as possible. So we want not just the National Geographic team, which is awesome, but what they're doing, we want everyone to be able to go out and explore like that.
Right. It shouldn't take, a big research grant to do all types of exploration. We think there's a lot that everyday people could do, for the cost of a DSLR camera.
But hopefully not following in the water next to the great white sharks.
Yeah.
We don't encourage that.
So I guess if there's interest, we could kind of show you a little bit more about it. The big idea is that we want to make this low cost but still really capable. So we kind of picture something that people could build in the weekend in their garage and use in their pool, but something that would still be capable of doing legitimate scientific research. So the main kind of part of the electronics for the ROV are all inside of this waterproof tube. And so you can see I can just remove it, and it's got the camera and motor controllers and some other guts. This is designed to be able to go down to about 100 meters of depth. Not nearly as deep as the bottom of the Marianas Trench, but that's deep enough to go where it's dark, where you see species you wouldn't normally see, and deeper than most scuba divers could go. We think that by giving people access to the first 100 meters of water, there's a lot of cool stuff that will come from that. We actually have a video of a recent dive we took with the ROV that kind of shows how it works. So I guess we could roll that. And yeah, there's a little audio, but it's just kind of the motors moving around. This is the Aquarius underwater habitat in Key Largo in Florida. It's an underwater sea lab that has aquanauts who live on board under the ocean for 10 days at a time. And so they invited us out to go drive around. This is from an onboard kind of GoPro camera we have that we're driving with, and this is one of my favorite parts. You can actually see one of the aquanauts inside of the habitation module. I think he was checking his email or something like that. So
it's one of the last undersea laboratories in the world.
Yeah, yeah,
it's pretty cool.
I think that this is the only one that currently is still working. So it's really cool, and
we were really lucky to go along with them, and we got to do some pretty serious ocean testing with the robot and actually see what was possible, and we were really excited about how well it performed.
Yeah, and then so the last thing about the ROV is that as I mentioned, we're all open source, and that kind of means we're crowdsourced as well. We've come up with a design that's kind of good enough, but what we really want to do is make it so makers and people like everyone watching this can come up with their own ways of making it better. We've got a payload module on the bottom of the ROV where you can mount robot arms or metal detectors or whatever you like, and all of the design for the hardware and the software is completely open source. So if you have a cool idea of how you could use this or how you can make it better, that's what we're all about, and we think a lot can come from that.
And it's a little misleading just to have Eric and I up here because we have hundreds of contributors all over the world who have helped us design the robot to what it is, and we welcome everyone to join us in the process.
We've got a question from the Open Robotics University. They want to
cool.
know, is the OpenROV ocean robot wirelessly controlled?
That's a great question. Actually, we get that a lot, and we'd like it to be wireless controlled. It would be a lot easier if we didn't have to deal with the tether. But the problem is that because we're sending live video, that requires a lot of bandwidth. And if you want to do that with radio waves, that needs a high frequency that just doesn't travel through water. So it is actually wired. And I have here what our tether looks like. A lot of ROVs have these really thick tethers that make them hard to drive around. But we've come up with a way of speaking Ethernet data over a very, very thin tether. In fact, it's so thin you can't even really see it with the camera. It's about the thickness of, I don't know, a noodle of spaghetti. But these two wires allow us to talk 10 base T, that's 10 megabit connection, down to the ROV and get video back up. Another thing that I guess kind of relates to that, we're not there yet, but what we're really trying to do is make it so you don't just have to be on the surface where the ROV is to control it, but we'd like to be able to control the ROV from anywhere in the world over the internet. So right now the ROV actually hosts a web server from the robot itself, and what I picture is kind of like playing, I don't know, World of Warcraft, where you can log on to some remote, distant world. We'd be doing the same thing, except for instead of flipping bits, maybe we'd be flipping rocks.
And the other thing is we do have quite a few members of our community who are really interested in making an autonomous OpenROV, and so they're working without tether. So that's the idea, is to make it autonomous without a tether.
Very cool. Thank you.
Yeah. Yeah. Any other questions? I guess.
Yeah. So can I ask you guys how is it actually made? I mean, it looks like it's a pretty interesting material. Is that acrylic, or how do you put it together?
Yeah, that's a great question. Well, the way that it's assembled, actually, I think is one of the keys in how we've been able to make it so low cost. We're using a device called a laser cutter, which is this really cool, really hot laser beam on a kind of a robotic arm. And you can program a drawing, and the robot arm will trace out that drawing and cut materials. So here I have an example. These are some parts that would be inside of the ROV, and it's a little hard to see with the camera, but as you can see, I can take it apart. It's a whole bunch of these flat pieces. And so OpenROV is designed with a bunch of flat pieces that fit together, and kind of like Lego project. It only takes about an hour to assemble everything. So you glue all the pieces together, and it kind of works that way. So laser cutter, and then we go to this place called Tech Shop, which is super cool. It's this place that has a whole bunch of tools that you can just use. You pay a membership, kind of like a gym membership, but instead of using a weight set and a bicycle machine, you get to use a milling machine and a laser cutter or a 3D printer.
We've done everything there. So they have all the tools that we've needed to make this happen. So even this clear tube, you can see the end caps are actually 1/8-inch acrylic. So it's all that flat acrylic that Eric talked about. We do have a fold here that we use a strip heater, and we kind of fold it down inside. So that really helps to get the shape that you see here.
The coolest thing about all of this is, I mean, once you have the right tools, you can look at any raw material, like a piece of acrylic or a piece of polycarbonate or a piece of metal, and you can turn it into whatever you want. And so what I always think of is, like, when I was a kid, I used to picture the cool things I could build with Legos. Legos were this building block, and I could construct anything I want. But when you learn how to use these tools and you learn about the capabilities you have, the world becomes your Legos. You can build anything you want out of anything you see. And so it's really cool because suddenly you're living in your Lego box.
And the other thing that I'd point out is that I didn't have any prior making experience before meeting Eric and getting involved with this OpenROV. So there's a lot of there's a lot of opportunities for even people who don't have a lot of experience to kind of get in and start making stuff. I have a question for the Nat Geo team. Do you guys have any tips or ideas of ways that we could make this thing go deeper?
Get out of titanium?
Probably. Most of our ideas would probably make it more expensive, but you can always get a thicker piece of acrylic.
Yeah.
Yeah, we were looking at making this tube out of borosilicate glass or something like that, or maybe backfilling it with oil. I guess if we start getting to 100 meters and shucks, we're getting there, now we want to go deeper, that's a really happy problem to have, and maybe we'll talk with you a little more.
I mean, making that center tube out of glass would probably be the easiest thing to do next. It would just, I don't know how much the piece of glass would cost necessarily, but the other way is, like, when you start filling things with oil, it works for like everything but the camera part. So you're going to need like a little camera enclosure or something that's still full of air.
So yeah, put your electronics in a bag of oil, and then make your camera housing smaller but beefier, I guess. Use thicker acrylic on.
So I have one other question. So what are some good locations that we should take the OpenROV and explore? The places where we can see a lot of really cool things at less than 100 meters.
No, it would be awesome taking an ROV to like some of these alpine lakes that like they go really, really deep and no one's ever explored them, and they probably had hikers like defrost falling into them for hundreds of years. Yeah. There might be some really cool stuff down there.
You know, I used to drive an ROV around Lake Tahoe, not this one, but I remember also, you know, the bottom of Lake Tahoe is just flat. It's all silty, and we found that, especially in the places where there's been tons of boaters over, you know, 50 years, almost always within moments of hitting the bottom, we'd immediately start seeing man-made objects, and not trash, but the kind of things that are heavy and that people can't retrieve. Pocket knives and sunglasses and, you know, who knows, wedding rings are all down there. So we're kind of excited to just go down and see what's sitting on the bottom. Maybe we can learn how to pick it up with the robot arm someone develops.
And that's another cool thing.
Man-made lakes too, where they've, you know, like flooded areas, and the, you know, the town that was there is now this underwater ghost town. So I mean, you just get amazing footage going through, you know, houses and water towers.
I mean, how cool would that be, right? You have your own city to explore.
So I think that's really cool because, I mean, you guys said that even every time you put this, you put your underwater camera down, you see new species, you see all these new things. We've had the same kind of excitement and experience, even though we've been going in underwater caves and lakes and reservoirs around here. It's just this kind of feeling of we don't know what we're going to see. I think with the quadcopters and all the great aerial images, you kind of know what you're going to see. But when you're going underwater, it's, you know, it's anybody's guess what's going to happen. So I think that's a really exciting aspect to what you guys are doing, but also to what OpenROV can do.
No, we really say that. We prefer our underwater. That's what the domain we like to stick with.
Yeah.
We've got a question from some of our campers for David and Eric. Deanna wants to know, now that the OpenROV is becoming available to the public, what kind of projects are you guys looking forward to being done?
Oh man, there's so much. I mean, one of the things that I think excites us the most is that like OpenROV, the community right now has members from across more than 50 countries. These things aren't just going to be around here where we are. There's some that are going to be in Indonesia. There was a guy in Taiwan, I think, who wanted to use it for fishing. We're going to start seeing what I hope to be like YouTube videos people create of, hey, I was just in this random place and this crazy squid-looking thing, you know, swam in front. What is this? And maybe we can get scientists collaborating and saying, oh, well, I think that's what this is. I mean, there's so much out there, and it's spread out so much that, I mean, there's no telling what can come from that.
So not only everything that we can see, but everything that we can still create. So this thing is all open source, and we've had so many great ideas for people who want to put payloads on it. So some people want to build robotic arms, other people want to build pH sensors, and all these different things that they want to, you know, add on and create with the OpenROV, and that's awesome to hear as well. And we just really, really encourage everyone to build whatever they want.
We'll take advice too if anyone has any suggestions. We're really, now is the point where we really want to hear where this can go.
Well, I think a lot of people want to know, where do they find the design since it's open source?
Yeah. So right now we're hosting our CAD files and software on GitHub. If you go to github/OpenROV, you'll be able to find that. A word of caution, a lot of it is still under development, and we're still kind of working out the bugs. So people who go there will find that some things are being modified still very actively. There are already, I think, close to 25 or maybe 30 people who have already downloaded the plans that we provided and are building their own, and we're really looking forward to their feedback.
We're just starting to get photos from all over the world from people building their own OpenROVs, and it's cool because we always assumed that they would look like this one, but they don't. Everyone's building them in all these different colors.
Yeah.
To get all these different photos.
Yeah, and then there's also, in addition to OpenROV.com, which is our main website, we've also now got, I think, wiki.openrov.com, and that's where we're moving a lot of stuff. We're going to start a Wikipedia, or not a Wikipedia, a wiki page that just kind of shows everything that we're doing. Definitely, we're ramping up on content right now. Documentation is always a tricky thing to do.
Yeah, it's just a few of us, so there's so much to do and so much to make and so much to get out to folks, but we're working really, really hard to make sure that everyone has them.
That's awesome.
Yeah, I've got a question for the Nat Geo team. I was wondering, Eric and David talked about using the laser cutter to make their tools and their machines. What cool machines do you have in your lab, and what are your favorite tools to use when you're kind of prototyping these cool robots?
Alan?
Yeah, so actually behind us, this is our machine shop back here. So we have computer-controlled lathes and computer-controlled milling machines, manual milling machines, regular manual lathes. We actually use probably the one that's used the most often is our computer-controlled milling machine. We make a lot of our parts out of that. A lot of our parts are actually kind of 2D also, but they might have slight contours and stuff like that. And we make most of our stuff out of aluminum or Delrin, which is another type of plastic. So.
And what is that prototyping experience like? I mean, how do you start with a plan and an idea in a sketchbook, or how do you develop the idea to the actual robotic imaging system?
I guess we sort of, like the overall concept, we sometimes sketch it up, but like on a whiteboard or on paper, but then we usually end up using a CAD package like Pro-E, or and then exporting it to with CAM software to something for the lathe or the mill. But the cool thing about the mill we're using for a lot of this stuff that looks really expensive is actually a pretty cheap mill. That, like, if you decide to ride your bike to work instead of buying a new car, you could actually afford and have in your garage. And it's not cheap, but it's compared to, like, when I went to college, all the CNC mills were at least $60,000, and ours you can get the basic thing for like $7,000 or $8,000. It's actually the Tormach, which is probably the most affordable like real mill that can. So
yeah. So what we do is we basically kind of go to the whiteboard and brainstorm about what to do, and we figure out what tasks we need to finish off a project like the helicopter, and then we kind of split it up depending on what our area of expertise is. I don't use the machines very much at all, so I do a lot of electrical design and software, and then these guys use a solid modeling tool called Pro-E. Mike does a lot of his own coding, and he's actually pretty good with electricity too. I feel a little bit challenged by him all the time. So
I've been trying to take your job for years.
But yeah, we basically just split it up, and then we kind of come back together at the end and do testing and eventually come out with a system that kind of works. So.
I've got a question that could go to either team or maybe both teams. Michael wants to know, how well do the motors work in very murky water, and do they ever get jammed?
Yeah.
OpenROV?
Well, I guess if...
For both.
Well, I guess we'll start out. We use these brushless motors. They're the same motors that you'd use in like a remote control airplane. And if I pull off the stator, it's a little hard to see with the camera, but basically it's just a bunch of coils, and those coils turn on and off and move a set of magnets on the part that fits around them. So there's really no thing to leak. Everything is just wound wires and magnets. So the two big issues that we have are corrosion and electrical shorting. The electrical shorting we can take care of because the wires are already insulated, so we just have to put liquid electrical tape over the solder joints. And then we spray silicone spray on top of the motor, which kind of keeps it from oxidizing very quickly. And because the motors are off the shelf, they're only about $10 a piece. If one fails, it's not a big problem to replace it. In our experience, we haven't had too much trouble with them jamming from rocks or grit getting inside. Sometimes you do notice it's a little bit grindy when you try to spin it, but spraying it off with fresh water seems to solve that problem. When we went to Nemo, we were in ocean water. We were in the ocean at 60 feet depth for an entire day, and everything seemed to work just fine.
Talk about the Lazy Susan.
Which thing?
The Lazy Susan, Turney.
Oh, the oil pump thing. Oh, that wasn't. Our problems haven't been clogging so much as other kinds of ocean destruction. Like we've had our crystals. Sometimes when we try to oil comp something.
Basically, we took a motor and we put it in an oil. We oil compensated it so that seawater couldn't get in, and that's kind of how we avoided the whole issue of shorting and having, because it's inert oil, doesn't conduct electricity. But as Mike's going to point out, there was other issues that come up. The ocean's really hard, it turns out.
Yeah, the ocean is hard. Yeah, there's a lot of ways for it to not work, and we haven't had the clog. We had a velocity meter that used to clog sometimes, and it actually clogged with a shrimp stuck through it. But That was something else. That's not really common. That particular, our Lazy Susan thing, well, it was part of the drop cam. One of the drop cams turned around and stuff. But we had it in an oil bath, and the little crystals would cave in after a couple thousand meters. And I didn't really test it that much. So Graham and I, who's not here, found out about this when we were actually doing a shoot for a movie. So what we ended up doing is getting a Dixie cup full of epoxy and putting the entire controller in there and just like setting it in a hard epoxy, and it made it get through the rest of the shoot. But and the other thing we have trouble with as far as ocean destruction goes is seals. Seals are evil. If you try to stick a camera on a seal, it will be broken, like for sure.
High attrition rate with seals for sure. Yep.
So that's an interesting question I want to roll into is what kind of gear do you have to pack when you're going on site to fix your camera gear? What what tools do you need to have on hand?
A lot of zip ties.
Yeah, a lot of zip ties.
Hose clamps.
Yeah.
Soldering iron.
Yeah, soldering iron. It really depends what you're taking into the field. That's the hard part beforehand, is thinking like what can go wrong and how am I going to be able to fix that. I was out recently in the Pacific Ocean doing some drop cam stuff, and luckily we were on a big ship and they actually had a machine shop on board, so they could do some light machining, which actually helped. But most of the time what we take out is just a basic tool bag with your screwdrivers and duct tape, electrical tape, hose clamps, rubber bands, zip ties, and that gets you through most small breaks.
Got a question for OpenROV. Joseph, one of our campers, wants to know how much heat builds up inside the clear tube.
That's a really good question. Thermal issues are a really important one to look at when you're in an enclosed container. They haven't been too bad for us. The whole ROV consumes about 8 amps at 12 volts, and so there's not a huge amount of power that we're dissipating. The lights are 87 lumens each. They go about 150 milliamps. So it's not too much of a problem. We're surrounded with water also, so that helps cool, even though the acrylic's not a great conductor. I guess in short, it hasn't been too much of a problem for us. I think if we start getting brighter lights, which may be necessary later, we may have to mount them outside. But yeah, generally it seems to be okay.
I have a question. How does having like a curved surface like the tube or like the spheres change your ability to take photos? Like what kind of features does that add or limit?
Nat Geo,
Yeah.
This one.
It does distort the image a little bit on our camera. We kind of like got around it by using a really wide angle lens and putting it right up against the glass to limit the distortion. But it is a problem, and we did have to think about that. I mean, we had to figure out how to get the lens really close to the glass, and when the glass squeezes together under pressure, to keep the lens from like getting pushed back into the camera. So it's always a problem. Underwater's hard.
There's if it's a spherical surface, there are like certain distances that will be okay. And the easiest way to figure it out is just to do an experiment, but there is software that can figure it out that we haven't actually used. So
we also had we had a group from Woods Hole that that integrated a 3D camera with us, and they used that fancy software, and it looked pretty good at the end, didn't it?
I'm not sure if they actually even used it either. I think they just did it.
They just did it. Okay, good.
If they you want to be like with a sphere, you want to be on like axis. You don't want to be like off to the side, and they were off to the side, but the distance was only like an inch maybe off axis. So, and they were also using wide angle lenses, so it didn't create like a really bad issue. I mean, on a wide angle lens, you've got this like the depth of field that's in focus is huge, so it covers up a lot of lens problems. It's convenient because most people want a wide-angle view underwater. So.
Cool. And we've got another question from a camper. They're asking, is the material used to make the robots biodegradable? And this is for OpenROV, I think.
Wow, these are really awesome questions. I'm amazed at these. They're not in our case. It's really hard to to build everything that way, because even if the structure was made out of something that would decompose, obviously the electronics, for the most part, we wouldn't be able to make that way. So there's kind of a risk there. I mean, the ROVs are relatively small compared to other ones, and also it's tethered. So, for instance, if the ROV fails, you should be able to just pull it back out through the tether. It's strong enough, and we've actually done that a few times. But you know, there's other options too. One of the things that I saw that James Cameron did after he filmed the movie Titanic, he went back to the Titanic to make a documentary, which he called Ghost of the Abyss. And he had these really cool ROVs that he drove from manned submarines that were outside the Titanic. He used these small ROVs to go into the Titanic and, you know, drive down the corridors and into rooms. And they were using a little fiber optic cable, this tiny little fiber optic cable that was actually held on board the ROV, and it spooled out from the ROV, kind of like a spider spinning a web. And that allowed them so that as they went around corners and things like that, instead of getting snagged, it would just pay out more tether. Mm-hmm. And even if it did get stuck, they could still drive the ROV all the way back to its home base, and if they needed to snip the tether, that would be okay. That tether was specially designed to be biodegradable, so if they did have to ditch it, it would be okay. And we kind of looked into things like that. And I mean, also our tethers, it's copper wire. It's somewhat inert, but you know, we just do the best we can, kind of.
So we actually get that question a lot, and people have said, "Aren't you concerned about, you know, putting more plastic in the ocean?" And absolutely. I mean, Eric and I both love the ocean and are very concerned about that. And the conclusion that we've come to is that the potential for losing an ROV and adding a relatively small amount of plastic to what's already being put in the ocean, unfortunately, is dwarfed by the huge upside of exposing so many more people to you know, all the issues that are going on with the ocean. So we think that the kind of the cost and benefit analysis is we think the upside is much greater, but it's definitely something we're concerned about, of course.
That's great. We've got another question from camper Deanna, who wants to know, for young people interested in underwater robotics, where would be a good place for them to start, and what resources could you recommend?
There's a bunch out there. I mean, definitely learning by doing is what I try to preach the most. I mean, you got to just get your hands dirty, or wet in this case.
Exactly.
I mean, if people want to start out with an OpenROV kit, we're hoping that, you know, this was something that's easy enough for people to build. Right now, we have a Kickstarter project launch. If you go to Kickstarter and type OpenROV, you can find these kits that we're selling. But there's also a lot of great projects out there for kind of a high school level, and I think it goes all the way down to middle school and up to college also, is the MATE competition. So that's a kind of a competition where students can build ROVs, and they all bring them to one place and compete in a common objective. And there's also some other kit ideas that are online. Even OpenROV has a lot of topics on how to build things that may not necessarily be used in our OpenROV, but are useful. My biggest recommendation, though, is just start putting stuff together. Make mistakes. It's cool to fail. Fail your way to success. So
we saw a video of a hamster-powered submarine.
Oh yeah, that one. That was so.
But there's another.
We don't recommend that. If you have a hamster, like.
You have parental supervision. But there's another small kit called the Sea Perch, which is another great OpenROV, or not an open, but it's an open source an underwater robot.
What's it called?
It's called the Sea Perch. It's good for like swimming pools and things like that as well.
Yeah.
Cool.
Yeah.
So it's interesting, actually. I'm curious from the Nat Geo guys. What is your background? Did you just start with cameras? Did you like animals, or are you just engineers by trade? How did you get into this field?
So actually, for me, it was pretty interesting. It was actually mostly random chance. I was in college. I have a degree in mechanical engineering, so I was going as a mechanical engineer, and I got invited to go to an archaeological dig in Jordan, just kind of out of the blue, and we were leaving like the next week for 3 months, and I ended up going on that and kind of started getting into this idea about archaeology and preservation, and how can I contribute to that with my engineering skills, and that eventually led me here. So that's how I got here.
I went to school in Washington, D.C., which is where our headquarters is, and I was working on actually a hybrid car project, and I used to make I used to like make as part of a grant, I made laboratory test equipment with CNC machines, and somebody on car project had actually been working here, and they needed somebody that was more experienced with making complicated parts. And I ended up getting a job here part-time, which paid better than my security desk job. So I stayed. But that was in like 2001, so it's been a while.
Yeah, I've sort of always been interested in like robotics and stuff like that. When I was in like 7th grade, I built a robot in my basement and went to Radio Shack and got all the parts and stuff. And then I went to college for electrical engineering and got basically my first job was doing underwater systems for Department of Defense applications, which is less fun than here. And then I had an opportunity and came here, and basically I'm the resident electrical engineer, so it's been really fun.
And I just get to write about these guys. So I write headlines, and I write blogs, and put up photo galleries and videos of what they do, and help get the word out about them through Twitter and Facebook and things.
That's awesome. Cool. What was the most fun mission you guys have ever gone on?
I don't know. I mean, it's hard to say. You go first.
I think fun and interesting are two different. But the most interesting one was probably the one where Mike fell on the shark. Not because of that, but just because of the craziness of the situation. There was like another shoot going on, and we were kind of piggybacking on this other production, and the other production was doing something crazy, which was like having mermaids and spear fishermen swim around with great white sharks, literally like a girl dressed as a mermaid. So that was.
This was not a National Geographic.
No, this was not National Geographic. And National Geographic did not know about this when we went, and so we were a little bit afraid we were going to end up in Mexican prison. But
we also didn't have what you call permits.
Yeah.
Which we didn't know before we got there until we were just in the middle of it, and like no one had any permits.
So we came back, and we really hated it the whole time, but then we were like, that was the most amazing thing ever.
Yeah.
But it's your.
We had some permits, but it wasn't for exactly the level of shenanigans that was going on. So it was just, that was wild. I would say like one of the coolest places I've ever been was it was probably in a fjord in Alaska, which is like this giant concrete canyon with a glacier at one end. And that was probably like the most scenic thing I've ever said, but I think the most interesting thing was the white shark thing. And the cool thing about the glacier thing is every day you woke up, and it was never really night, everything looked different because the ice had moved all around. But anyway.
I was in Kyrgyzstan. That was pretty cool. We were searching for Tamerlane. He was an ancient Mongol warlord, like looking for his underwater palace. And so we were kind of just like splashing around this lake, like, you know, with masks on, looking for this thing. That was a pretty fun project to be on.
That sounds awesome.
Yeah, we got to go there with OpenROV.
Yeah, that sounds
that would be a good place.
What's the coolest mission you guys have gone on?
We just recently, well, I mean, there have been a few. Nemo is pretty cool, but one I really liked is there's this underwater cave way up in northern California in the Trinity Alps, and there's stories that there's lost treasure that got thrown down this like bottomless water-filled pit, and no one had ever really explored it. So we went with OpenROV, like carrying these Pelican cases the first time through the snow, and we found this cave, and there's just this like crystal clear blue pool in the very back of this cave, and so we set up this whole operation station in the cave with like a Foldy table and computers and lighting systems, and we dropped the ROV in and started driving around through these underwater caverns. And I mean, it was just, I mean, it's like something that someone would make up for a movie, but this stuff really exists. It's out there. You just have to go there and check it out. So that was really cool to me. I liked it.
That's awesome.
What is Nemo, since you've mentioned it twice, and I know it's probably not a movie about a clownfish?
No, although that one's also really cool about underwater. But so I mentioned the Aquarius underwater habitat, which is run by NOAA. Nemo is a mission that NASA does at that underwater habitat. So this is Nemo 16. And
so it stands for NASA Extreme Environments, Mission Operations or something like that. So it's simulate. Is that right? I don't know. Maybe it's something like that. It's something about extreme environments. But they're trying to simulate what it's like to be kind of in space or on the space station, so that this is a perfect environment for them to train astronauts and aquanauts.
Yeah. And it was cool. I mean, the thing that I really liked about that, I mean, it was neat to be at this crazy underwater sea lab, but the visibility in Key Largo is just amazing. It was like swimming in an aquarium. There were just fish everywhere, and barracuda and other fish, and they're interacting with each other. I mean,
and even the people who've been there for doing it for 10, 15 years said the specific day that we were out there was the best visibility that they've ever seen. So
yeah,
it was really cool.
But the thing that just that excites me about underwater and kind of continuously is, if you're just used to being a person where you're looking at the water from above it, it just looks like some waves, and you can't really picture that there's that much going underneath. It's very easy to be a bit naive about that. But once you have a glimpse from below those waves, you realize just how much is going on there, and there's so much that we haven't seen. The ocean's three-dimensional, and 95% of where life can exist on this Earth we've never actually explored. So who knows what crazy, giant squid or weird-looking worms or whatever are down there, and they're just waiting to be looked at.
That's awesome. I've got one more question for Nat Geo from Bob. He wants to know, can you tell us about one of the most complex or difficult engineering problems that you've encountered, and what got you over the hurdle?
I guess the one we're on right now, right? That's and we're not over the hurdle yet. Yeah. We're developing we're basically taking the drop cam and we're putting something called a buoyancy compensator on it, and it's sort of like what you'd have if you were scuba diving, but it's going to be able to go 1,500 meters down. And as the OpenROV guys were discussing, moving parts in the ocean is a difficult problem, and so we think we have kind of a solution for it, but we had to do a bunch of math and stuff we don't usually do. But yeah, maybe you guys can talk a little bit more about the system that we're proposing.
I guess we had a couple constraints because we're trying to have the drop cam sit around at very specific levels in the water for like weeks. So we had to do it where it doesn't use too much power. And also, if it's going to be there weeks, things start to grow and stuff in weeks. So if we have like seals that are like dynamic seals that are exposed, it's like not impossible, but it's less preferable than like it could be. So we had to design it so that it wasn't going to foul. I mean, it could sit in the water for months. So and some of the stuff you'd be surprised how quickly something turns into like a coral reef in certain spots. And you have like barnacles and stuff growing on it. But anyway, the other problem is it's just a lot of force. At 1,500 meters, like even though it's not full ocean depth, some of our like one of the components is a ball screw, and it's going to have like 7,000 pounds of force on it, and it's I don't know, to have it not jam is hard.
Yeah, I think part of it's stepping through the problems. Like that's how we're approaching our current problems right now with this buoyancy compensator. You start out with kind of a theory something that you want to do, and then you're going to outline a way to accomplish that. And so you have to. There's a lot of you just have to be able to visualize kind of like what's going on, and then figure out ways around that. And a lot of times it's me just sitting there at my desk, and it doesn't look like I'm doing anything, but I'm just thinking really hard, like how am I going to figure this out? So it's just a big mental exercise.
The other thing is we have these weird constraints where we have to get the stuff on planes, and my initial plan, that probably was a terrible idea, involved like highly compressed gas, which they would never let on a plane. So like there's all those things. Like once you make something, you have to take it to where you're going, and a lot of my plans usually don't involve it passing onto a plane without like a national security violation. So
you need to check. It needs to fit in checked baggage, which is a kind of an awful constraint for an underwater system. For us,
we've had the same problem. We've had so many interesting conversations with TSA agents.
For some reason, sealed tubes with wires coming out of them are a concern.
You guys need a private plane.
Yeah.
Yeah, let's work on that. All right, we'll get back to it.
Open airplane, right?
Yeah.
Open source.
So with all these constraints, both teams are working on. We can start with National Geographic and then move to OpenROV. But what does everyone think that the cameras of the future will look like? Moving forward, what's next?
I guess one of the projects we're working on is color night vision, like true color night vision, like the night vision you see on CNN when they're dropping bombs on somewhere. It's kind of green and grainy, and we're cooperating with an explorer we actually have here to build a system that will use a lot of computational photography algorithms to take standard night vision and make it actually 3-chip color, so it'll look like day, like when you're shooting the lines in night. It'll look a little grainier, but
yeah, it's trying to take the suck out of it with computers.
Yeah.
That's what we meant.
Yeah.
I think also like one of the things that's well, I mean, it's already happening with OpenROV. It's just more cameras in more places, and I mean, like we've got 5 drop cams, and we made the drop cam to be a cheaper alternative to large-scale boat exploration. And there may be at some point tens of them in the world, or 50, but there will never be as many as there are with the OpenROV thing because it's actually far more affordable. I mean, there could be thousands. So I think sort of the future is more.
Yeah. More and cheaper.
More and cheaper.
Cheaper and deeper.
Yeah, that's what we always say.
Deeper and deeper.
And so there's so much cool stuff that's on the brink of technology. I mean, the cool thing about what's happening right now, I guess it's actually kind of part of the make movement, is that suddenly individuals are empowered with the same type of technology that would normally be really hard to do. 10 years ago, for instance, you couldn't get a Linux computer that can host a web server and HD video to fit in an Altoids box, and that's what I've got here. That's what's on board our ROV. One thing that I'm really, really excited about is this subject called computer vision. Some of you guys may have seen kind of the popular examples of computer vision, which are like, how a lot of cameras these days will recognize a face, or like Facebook can recognize a face compared to other things. That's computer vision. It's a computer looking at an image and figuring stuff out about it. So, for instance, could we say, I want you to recognize all seashells that look like this, or I want you to recognize a pattern in the silt and the striations, and maybe that's a way of keeping the ROV going in the same direction. There's another program I've used in OpenCV. It's a computer vision program where I can put my finger in front of a screen and then with my mouse click on the tip of my finger and it'll put a little green dot there. And as I move my finger around, the green dot stays on my fingertip. So if we can do that, maybe we could click on a lobster and say, follow that lobster. So I think computer vision has huge potential for the kind of ways that we can kind of do high-level exploration, where you could have a fleet of ROVs all searching for something, and the ones that find something interesting can get back to you, or they can follow each other. There's just so much there.
Yeah, and yet another thing about that is we're also starting to experiment with different photogrammetry tools. So actually, we've been using Autodesk 123D Catch, which is free software, to try and generate 3D models from a series of images, right? So it's not just what the camera can see, but also what you can create with those images and with those things. So we've had some success with that so far, but there's tons of potential, and we're looking forward to doing more of that as well. So imagine going out with a couple of ROVs and then coming back with 3D models of the coral reefs that you just explored. So, but just a few ideas.
Yeah, awesome. Jillian, do we have more questions from the campers?
I've got one more question from camper Kevin, who wants to know, have you found any species, or are there any really exotic animals that you've seen?
Yeah, so we were recently out at the Pitcairn Islands in the Pacific Ocean, and we were using the drop cams out there, and we actually found a bunch of new species actually that hadn't been seen before.
8, right?
Yeah, eight new species. So that was cool. One of the coolest things we saw too is there's this fish called the Pitcairn angelfish, and it's really rare. And yeah, there's only been a few pictures of them taken. And me with the drop cam, and there's another guy, Enrique. It was kind of a race to see who could get an image of it first. And yeah, drop cam did. So woohoo! But yeah, so that was pretty cool to be able to find all those.
How can you be sure that you found a new species no one's found before?
Yeah, tricky, right?
Yeah.
So basically a bunch of scientists look at our video and imagery, and they see that that species has never been photographed or described in literature. My understanding is to actually declare it a specific new species and give, because we'd love to name, like I'd love to have the Eric fish, but unfortunately we have to bring a dead one up and or a live one and take a DNA sample and actually confirm that it is a new species and isn't just like a funky looking carp or something.
So kind of a low impact DNA sample would be a good arm to add to the OpenROV.
Yeah, we'll keep
anybody out there.
We've actually been talking to some of our folks who do like DIY bio stuff. So people who built the OpenPCR and the Open Gel Doc system, and we're trying to create this whole open source tool chain to do exactly that.
That's cool.
Yeah.
So if you could, Eric and David, if you could dream up like any feature to add to the ROV right now, like what would you add tomorrow? You know, any feature you could dream up.
I mean, like going beyond the kind of what we're already. I mean, I think when we get robot arms, it's going to be really cool. But ooh.
Yeah, robot arms as well. And some kind of manipulator would be really.
Yeah, that's just what goes through. We have like right now. I have this. We actually went to this science hack day in San Francisco. It was super cool, and we kind of crowdsourced this. This is a water sampler that goes on the bottom, and this is really interesting if you want to take water samples. It's just a tube. Let's see, I'll hold it up to the camera. It's just a tube, and there's these little rubber plungers and a kind of a spring trigger mechanism. So if we run the ROV into something, it closes those plungers, and we can take a water sample. So, you know, I think once we start getting these ROVs out into the hands of a lot of people, like we're just going to see all these crazy things that people are adding onto the bottom. And you know, I guess I'd like to change my answer. What I'm most excited about is the things I haven't thought about yet.
Yeah.
Because, yeah, I think what other people are going to start coming up with, this whole crowdsource thing, that's going to be super cool.
Good answer.
Yeah.
We're going to buy an OpenROV, I think.
Cool.
I was thinking once you get to go a little deeper, you should get somebody to do OpenROV Garage, like a little thing that you can lower it down on, and it like takes up the cable.
Oh, yeah. We thought of this thing. It would be like a pontoon boat, kind of, where the pontoons would be on either side of the ROV, and there'd be like a gantry in the middle, and that would be completely remote control. It has like a Wi-Fi hotspot on top, and yeah, we were picturing just being able to stand on shore and drive it out to wherever, or have a GPS autolocator, maybe satellite link at some point. If you guys have any resources there, let's talk. I mean,
Okay.
Cool. Well, I think I want to thank everybody from the imaging labs over at National Geographic and OpenROV. From National Geographic, what is the best way for people to get more information? Do you have a website or like the Google Plus page if you want to learn more?
Yeah, that would be a great place to start. You can follow us on Google Plus, and that's where we post the stories and videos from these guys, and it's an easy way for you to keep in touch with the latest that they're doing, and that'd be the best spot. And just go to nationalgeographic.com, and you can search around and find all sorts of related materials.
Awesome. And how about Dave and Eric, for you guys, what's the best way if we want to learn more about OpenROV?
Sure, yeah. The best way is going on the website, openrov.com. We do have the Kickstarter project up. There's a lot of good information there. If you actually want to contribute to the project, we have the wiki up, which is a great source of information, and also GitHub if you really want to start diving into some of the software electronics. We welcome.
And then we're also on Facebook, Google+, and Twitter.
Yeah, well, everywhere.
Great.
Or you can email
thanks again.
David or Eric at openrov.com.
Yeah. Perfect. So thanks again to Jillian and Josie for the awesome questions. And everybody, before we leave, I want to do a shout-out. There's about 300 kids over at the Maker Faire Detroit right now. They're doing some the Detroit Public School System, the Latino Mission Society, Laser Adventures and Learning, and the Delray Community House. So thanks for watching, everybody, and joining in with the questions. And remember, there's a Junior Counselor Hangout afterwards. If you want to hang out, ask us some questions about the projects we've had over the last 2 weeks. We'll be releasing the next week's schedule pretty soon with the materials you can follow along. And as always, if you've built these projects, you want to share your pictures, use the hashtag MakerCamp. We'll be happy to check those out and reshare them from the Plus Make page. And again, there's the school shout-out. So everyone, thanks for watching, and we'll see you next time. So thanks.
All right. Bye. Thanks.